welcome everybody. Thanks for joining me here. And so I'm going to, I wanted to talk to you about challenges that I have been facing and I am facing, and how I, working together with everybody else in design teams, how we solve those, approach those challenges, and how that leads us to a bit of innovation in the design process. And so I'm going to go through a couple of projects that I've worked on. Then I'm going to move on to timber and the Metropole parasol, go through that project in a bit more detail and the challenges on that one. And then I'll finish off with some of the challenges that await us in the future, and the steps that we're taking towards those challenges. Just to complement my biography a little bit, I was originally born in Germany, but I grew up over here in the States. Then we moved back to Germany, and I went to university there, and started working for Arup in 2000, originally in London. Then I moved to Madrid, to Spain, and 4 years ago I moved here to the Bay Area, where I now live with my wife and son. And in my kind of life, in that same biography as an engineer, I think I started off as a contractor, because first I started building. I started building especially trains in wood, the brio. Then somewhere in my teens I kind of moved over a bit into manufacturing, fabrication side of things, and I tried to whittle letter openers and knives, but that didn't work out really well either. And then I moved into structural engineering. And here I am on the side of the Metropole parasol. And I found that engineering actually is what I enjoy doing most, and where I enjoy trying to solve challenges and to keep challenging myself. So to start off with some of the first projects that I worked on, especially in the first 5 years in London, and I worked on a wide range of projects, but there are a couple of common themes which which slowly formed to what I focused on in my later years. This is the Paul Klee Zentrum in Switzerland, which we did with Renzo Piano Building Workshop, which is a series of 3 hills in the landscape. And where I learned early on that geometry is key. In a lot of projects, geometry is really important in defining a clean and sound basis from which you can then move on and find structural and architectural solutions. And so, early in my career, I noticed that, together with the architect in a common, it wasn't really a common BIM model, because, interoperability between software and us working in Rhino and the architect in AutoCAD, it was still, a bumpy road, but the intent was there to actually, to start off with one geometric model, which we use for the entire building. And here you can see the finished product of the steel arches and the undulation, and how they go back into the hills. Another project where geometry was also very important, but also constructability. And my first foray into, coming up with swinging geometry is all good and fun, but you also have to make sure that it's actually something constructible. Geometry still plays a large role, right? If the geometry is simpler, then the fabrication is a lot simpler. And here, in working together with the architects in even if it's this torus, this donut is has a radius which is immense, but you boil it down and you use tiny elements of that larger geometry to get down to the geometry of the building, and then move on to actually coming up with a solution here, once again in steel, of this grillage which you can fabricate. Once the geometry is defined, you sit down with fabricators sometimes early on to come up with a solution for these canopies. These are canopies in Portugal, down south in the Vila Moura, for a port, for a yachting marina. And then at the same time, not just purely concentrating on the geometry, but also working, so how does looking at the geometry and trying to figure out the geometry, how it influenced the structure, and how an architect and an engineer working together with the same geometry and the same model, how does that collaboration, can we actually take it so far that two of us sitting at the same desk working at the same computer, would that actually be a worthwhile effort? And I teamed up with Andrew Marr, who's an architect from Australia, who was doing research and collaboration of design teams, and we decided we took a project. This is a bridge linking the Selfridges store in Birmingham with a neighboring building, and we decided, okay, I'm going to come up with structural criteria. He's going to come up with his architectural criteria. We're going to work on one model together. At the time we used CATIA, and we're going to try to optimize the structure to fulfill both of those criteria. It was the first run, and it kind of worked. We were also very lenient with our criteria. Right, I wanted to have minimum deflections, and he wanted the aesthetics of the form. In the end, the solution which was closest in the work that we did, both of us were kind of happy, but we did notice that it was almost nearly impossible to 100% fulfill the two criteria that we had set up at the beginning. But nonetheless, it was a really good experience, especially sitting next to each other at the same desk and not communicating every now and then when the need arose, but actually four hands and almost from one body. And that kind of collaboration, team effort between engineering and architecture, we took that a step further with a project in Hong Kong. There's the West Kowloon Cultural Development with Norman Foster, where at the time it was all one big development. It was one big project with all the museums and everything, and it was all covered by one large canopy. This canopy is about a mile long, and we set up and this was during the competition phase for the developer, and we set up a project office at near Foster's office in London, where three of us from the engineering team were working together with the architecture team. And it was dictated for practical reasons. We had a timeline, we had a lot of things to work through, but also in just trying to find the most efficient design process and ensuring that all ideas are always thrown back and forth, and kind of lighting that design process and trying to get as many ideas out of it as possible. And so you can see we had a big pin-up wall where at any time, where even if we were working by ourselves, it would go up on the board, and then we'd have almost every 2 hours spontaneous discussions at the board to go through what we were working on, or just get together spontaneously at the table and try to find solutions for all of these structures and that canopy. And on that project, it worked really well. It worked very, very well. Maybe because the design criteria for the project were set by the client, who had his list of I want this, 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 and a lot of them were more defined by architecture, others by engineering, and we had to work together to a combined set of criteria set up by the client. Moving a little bit into parametrics and optimization. This is another collaboration with Australian architects and a pavilion with a random geometry and then intent of optimizing the nodes, where the common geometry and an engineering analysis model through an optimization process then actually define the geometry of the nodes. So you can basically what happens is that where there's more material is where the forces are going through based on the geometry of that random pavilion. So each node is completely different. But also each node is is a lot lighter, so we're saving a lot of weight because we're only putting the material where it needs to be. And we built a 1:50 prototype, which actually fit in his suitcase. So he came from Australia here to San Francisco to Fort Mason at one of the Autodesk conventions, and he packed it into his suitcase, came over, and then us architects and engineers together, we set it up, the 1:50 version. Here we then found out that, or one thing we had not taken into account at all, the erection sequence was actually quite critical, because cutting and milling all of the individual, 3D printing all the individual nodes was easy, but then actually putting them together while looking at the Rhino model on screen was pretty darn difficult. And we also looked at the material for this structure, and these are all straight wooden elements, and so the fabrication of those was also very straightforward. And so so this little wood pavilion takes me over to timber, and to put it into perspective, this is kind of a historical timeline. So this is back 2,000 years ago, and this is 500 years ago. And it seems that actually what we're doing in timber construction, we're getting smaller and smaller and smaller, and we're not reaching what previously was done with timber in the built environment. There's temples in Japan, actually older than, this is from the 12th or 13th century. There's stave churches in Romania. There's windmills. There are windmills in Germany. This is about 100 meters tall, which are now being built, so we're slowly getting back to that. Yeah. But timber can also be used as a reused material. You don't always need a new material. So there's a lot of facets of wood which fascinate me, and where we can actually use it a lot more than we're applying it at the moment. This here is a sculpture in Seattle, and it's wood from an old schooner, from an old boat, which was put together for a sculpture. There's a lot of engineered wood products out there. This is laminated veneer lumber, which has a lot of possibilities. I'll show that later for the Metropole parasol. But even normal residential construction, something which here is just normal stick frame, but can be used with CLT. In Europe, a lot of these buildings. It's not something fancy. It's not something special. It's important residential construction built with cross-laminated timber. So there's a lot of offices too. This is an office building in the UK for B-Sky B with glulam columns and beams and CLT floors, and then a solution. Oh, sorry, am I not close enough to the mic? Yeah. Or I can move this a little bit. Yeah, no problem. And so, in some of the in Europe and in Canada, we can see there are projects which are taking us up 20, 30 stories with wood structural solutions. I started working with timber also back in 2002. This is the Chiesa Futura in Switzerland with Norman Foster. It's completely a glulam beam and column structure sitting on a steel raised table. This is a kind of first BIM model that we had for the geometry and defining the areas of common curvature. And here's the timber structure where we also worked with the fabricator in figuring out what is actually possible on the fabrication side and using those limitations to come up with our structural system. Here, the strength to the self-weight to strength ratio of timber was really practical because since we were up on stilts, we wanted a lightweight structure. And also for the cladding, we also used wood. This is larch from same altitude, larch trees cut by a shingle fabricator 2 villages over. And then this is the larch that was used to clad the entire wooden structure and to protect it from the elements. And then 2006, I started working on the Metropole parasol. This is in Seville, in Spain, for those of you who haven't seen any of the images. And it is basically a large shading sculpture to shade a large plaza down in Seville. The original site, when the design competition was announced, was actually a parking lot. So this is the square in Seville. And first they thought, well, okay, we've got this, we're just going to build a shopping center. And so they immediately started excavating on site, and then they found these Roman ruins, which shouldn't really be a surprise, because in Seville it was an old Roman colony, and so you dig down 15 feet and you immediately encounter the Roman ruins. But it was good, because then the politically, there was a new mayor who was elected, and he thought, wait, up in Bilbao they have this beautiful Guggenheim Museum, and now Bilbao is all of a sudden on the map. I want something similar down here in Seville. So he announced this design competition, and we entered with Jürgen Meyer, an architect in Berlin, at the time more of a local young architect, and with this competition submission we won the design competition. And here you can see that what the original competition submission is actually different from the final, from what we built, and I will take us through that design process a little bit in more detail. So the team composition was also quite interesting on this one. So the architect was from Germany, Jürgen Meyer, ourselves, Arup, for the engineering from Madrid, together with other offices. And it was organized as a concession. So there was a concessionaire who won the project from the city and had 40 years, a concession for 40 years to build it, maintain it, and operate it. And that was our client, Sathir, who are more in the market for highways, bridges, like heavy-duty civil concrete work. But nonetheless, they tackled this, and it proved difficult, but in the end we also managed to work with the contractor. Quick overview of what is actually going on. So in the basement, the museum incorporates the Roman ruins that were found on site. At street level, the entire plaza is refurbished. An old marketplace, which used to be there, fresh produce market, moves back in at street level. Then there's an elevated plaza over it, over the farmer's market, and then we have the parasols who shade the entire square. And yes, at that competition phase, we were actually thinking more about a steel structure, and we think we had these cores or these trunks for the parasols, so we thought we could make those out of steel structures and then cantilever out and then connect the cantilevers, kind of forming a space frame. But it was all based on cantilevers, and cantilevers aren't the most efficient structure. And this was also a separation of structure and cladding, right? It wasn't really wasn't a holistic concept for this shape. So we started exploring many different kind of structural solutions for these parasols. Looked at single layer curved structures. Also went into looked at some doubly curved structures, and then finally moved away from the concept of having those individual trunks or stiff cores and branching out to a more one grid, one concept over for the entire parasols, almost like defining one grid and then just shaving away to form the final geometry. And at the same time, talking with once again, including the timber contractor, and kind of based on those balsa dinosaurs that you get in the flat pack, and then you take them apart and you put them together in that interlocking fashion. So you're using really simple elements to actually come up with a very difficult geometry. And the contractor loved that because all of the elements basically just have single curvature and can be cut out of rectangular panels. And so the original competition scheme actually changed, and then we went back to the city and said, hey, look, that steel structure which we came up with originally, that's not what we want. We have a more lightweight structure. This is also right. The parasols are mainly carrying their own self weight, with a bit of live load from walkways and a bit of wind. So once again, the self weight to strength ratio is really important. Maintenance is, we also took care of that by coating the timber with a layer of polyurethane, and so we then presented the city with this structure, this solution, where the first reaction was like, wait a second, what, timber? You want to build something out of wood? Because in Seville, nobody builds anything out of wood. But we managed to convince them, and then we moved on to start defining the structural solution, and especially the connections for the parasols, the connections between the elements, because the comparison I had previously to the interlocking, that intercombing, that doesn't give you enough stiffness, and you can't really transfer forces for the spans that we have for the parasols. So we had to come up with a solution which could transfer the forces, but also did not add additional weight to the structure, right? Usually, we just insert steel bars and then you transfer the forces, but all that steel that we would have needed would have put more weight into the structure, and then we would have had to increase the size of the steel, and you get into that loop. So we had to, look into variations of, cutting away wood, or on the far right, there's even, using instead of steel plates, actually using wooden plates, and trying to find something that respected the original geometry, was lightweight, and could transfer the forces. And then we, talking with some epoxy experts who were mainly doing research in doweling steel bars and epoxying them into concrete, why not do that with wood? Why not insert the dowels directly into the wood and transfer the forces with epoxy? And we came up with a concept for that, and then built our first specimen there, which we then started to test, because there was no values, there was no code, nothing to really tell us how much, what kind of forces we could transfer. And first test failed. The wood is what actually failed, and wood gives you a brittle failure, right? So a failure without warning. So we changed the grade of the steel and ensured that the steel, which gives you a ductile failure, would be our failure mode. We also had to test it for heat, right? In Seville, it gets really, really, really hot. It'll be 120 in the summer. And then, of course, also the radiation onto the steel and how it transfers down the steel rods. But epoxy is an interesting material. We had to consult with some experts from other fields and bring them in. You can cure epoxy on a molecular level and tell the molecular connections to actually resist a higher heat. So you put them in a kiln, basically. You turn up the heat, the temperature, and then it's a curing process of the epoxy. You leave it at that temperature for a while, and then it actually resists that temperature which you've fine-tuned it to. And that happens on a molecular level, actually. And so that way we could ensure that it could also resist the temperatures down in Seville. That was a really tricky one to convince the client, because they were kind of old school engineers sitting in the city building department, and luckily one of the main engineers there, he was kind of mulling about the idea. So you're not doing a mechanical connection, it's actually a chemical connection, so how does that work? And the chair that he was sitting on luckily was a brand new chair, had no bolts, and it was all glued together, and he's like, well, I guess if the chair that I'm sitting on works with chemical connections and glued together, then the parasols will work too. So it was actually pretty easy in the end to convince him. And so we moved ahead, and once we had the solution, we went on to an optimization. And okay, now we know how we can transfer the forces. It shouldn't be too heavy, but we also don't want 10,000 different connections. So we want to set up a kit of parts, and then each connection is assigned a connection from that catalog, basically. So this is the first catalog we came up with, which just had 6 different connection types. And as we moved forward, we found out that we actually had to expand that to different connections. And they're not only based on the forces that they transfer, but also the thickness of the wood element that we're actually connecting to. And so here's this is the beginning of our of our BIM model and the optimization loop that we went through. That's the architectural model in Rhino. It was fantastic because Jürgen did not change the geometry once in 5 years over the entire length of the project. They defined it in Rhino and said, look, we need something that's constant, and they didn't tweak it once, not at all. So while you might think, oh well, that's a pretty difficult constraint, it was actually really good because it was you had something which was fixed and unmovable. So we imported that into our analysis software, GSA. Quick description of the software: it's basically a two-way spanning grillage of beams, but due to curvature, we also get some shell action. For in-plane stiffness against some of the wind forces, we also have steel diagonals which crisscross between the squares. We tried to leave. Place those underneath the walkways, so there's walkways on top of the structure, so that the visual impact would be minimal. Then you can see the four wooden trunks, and in the middle there's actually the parasols kind of open up, and there's a cafe at high level, but that's a separate structure due to the high live load and fire resistance criteria. And so there we have a steel concrete composite structure and concrete cores, which house elevators for access and also for services. And so to actually optimize and define all of those connection nodes while always taking into account the weight of the connection, we linked our structural model to an Excel spreadsheet with Visual Basic. And then basically we started at step 0, and we gave all the elements the same thickness, and we gave them the simplest connection, and then we ran the analysis, and then told the spreadsheet to check each node for the resistance that we found out through the testing, and if the force was higher, then it would take the next highest connection out of the catalog, insert that into the structure, and then we would go back into the analysis model with updated timber thicknesses and new connection nodes and new weights, and then it would recalculate the structure. And it did that 82 times. And after 80 calculations, it converged, and it was equilibrium between the structural resistance and the weight of the structure. One parameter which might have been, would have made it a lot more complex, but would have been nice to also be able to tweak in this optimization process is the spacing of the beams. But the geometry was fixed, so we didn't touch that, and they're spaced at 6 feet on center. And then what we basically did is for the contractor, for the timber contractor, we sent him the Rhino model and spreadsheets. Sorry, that's why I'm including one spreadsheet in this presentation. Basically, that structural calculation spit out 12 spreadsheets for the different load combinations, and then we literally did not submit a single paper drawing to the timber contractor. one Rhino file and 12 Excel files. Mind you, the Excel files were about 700 megabytes big, you know, a lot of data in there, but nonetheless, that's all they got. And then it went straight into fabrication, right? They fed it into their system. They used from Rhino into BoCAD. There you can see one of the overall panels of the Curto laminated veneer lumber, which is the engineered product that we use. And there you can see the cookie cutter layout of the individual elements. And there you can see it being prepared in the shop and then covered with the polyurethane to protect it from the elements. And you can see it lying on site, waiting to be installed. And then moving ahead, the trunks were constructed first. It was pretty tricky because 2008, there was the economic crisis in Spain, and luckily this was pretty much exactly where we were in 2008. So we were far along enough that the city didn't cancel the project, but at the same time, they were also always grilling us about every single design decision. They always wanted to make sure it was the most efficient and the cheapest. So they're kind of always, while we were tackling this structure, which we didn't at the beginning, we were still looking for the solution. At the same time, they were always coming in and asking us, is this even feasible? Can we even build it? We're always, yes, we don't know exactly how, but we're working on it. So when these first 4 elements went up, obviously, it was a huge sigh of relief on our part to have finally gotten to where the client would just leave us alone and just say, okay, now just build it. But that wasn't true either. The south of Spain, very political, and then once people saw the timber going up, they were like, what is this monster? This is ridiculous. We don't want this in our city. And then the discussion started, and there was a lot of negative press, and we just kind of tried to, heads down and let's finish it off. And so here, about a year later, all the trunks are finished, and we're starting with the actual upper area. You can see how some of these elements they're pretty darn big, right? 3 times taller than this, and that's a strapping, 6'10" Bavarian timber contractor. And then they built everything on scaffolding. The temporary condition was obviously very, very important. It's propped temporarily pretty much at every 3rd to 4th node, and the scaffolding also offers that, but also offers a working platform at high level for them to store all their tools and everything. And so slowly from each trunk we built outwards until all of these areas started connecting each other. Another advantage of our BIM model and the Rhino model in the spreadsheet that we sent them is that we had built it once before, and I think I got about 2 RFIs on this project. The timber contractor just he went out there and it just built it. It all fit together beautifully, and there were minimal glitches on site. That went really well, which is good because we then got a political deadline. Before the next election cycle, right? There's a 8-week period in which no politician can, partake in any public act of opening a construction site because it could be seen as influencing the politics. So there was this kind of period, and so on the 23rd of March, we basically had to have this project finished. So it was quite tricky, but luckily the contractor moved ahead pretty fast. Here you can see almost I think that's actually the last piece way there back in the background in the crane hanging, the last piece to be put in place. And then I think on March 22nd, they took away all the scaffolding, and then the parasols were pretty much finished. And here just 1 or 2 last pictures of the square actually in use and not as a derelict parking lot. the walkways up on top. On the right-hand side is the cafe, where the structure then opens up, and then the walkway that goes over it. And the connections are all they're visible. There's no like plastic, little plate that covers it to give it a flush finish or anything. Jürgen we spent, 6 months developing this connection, and it's an important part of the parasol. So he also wanted it to be visible. So that project, it kind of showed me that even if the solution at the beginning isn't completely clear, even if all the design team members and the client, and at first it seems like it's a very difficult team, the political environment was really tricky in trying to influence us. If you just put your mind to it and keep challenging yourself, then you can actually come up with a solution and finish off a project. In the end, it took 6 years. I was in Madrid for 7, and 6 of those were almost working full time on this project. But of course, on opening day, all of us were together, having champagne and smoking cigars up in the cafe. And so moving forward to some of the other timber projects that I've worked on, and I'm now working on with Outlook down the road. This is the Life Cycle Tower in Austria, which we also developed with a contractor. And here it was about finding a modular, prefabricated timber system for office buildings, and looking at hybrid solutions. So we have a concrete slab, but we're using glulam beams, and we're prefabricating these modules with the idea of once you go on site, you're super quick. And we actually did. We built a story a day. So the concrete core went up first, and then the rest of the building went up in a week, right? With minimal environmental impact because it was quiet, because you're basically just doweling and nailing wood together. No dirt because everything was prefabricated and pretty clean, and minimal tolerances. So really good, a lot of advantages and actually speed to market and getting something done, but very dependent on fabrication, manufacturing, and the whole supply chain for getting this erected. So if the market isn't really there yet, so how can we kind of push more timber and more wood solutions to be applied in the market, in the built environment? Government support at the moment. The White House is spending $2 million. There's a project in Portland, the Framework building, which is an 11-story residential tower, and there's one with Shop Architects in New York. We're on both teams, and the additional money needed to overcome code hurdles and approvals and also testing is being funded by the government. They're saying that wood actually is a material. It's under the USDA because forestry is actually a type of agriculture. It's a product, and they want to support that industry. And for both, we're going further, and the lateral system, the cores, are also with wood. So there's nothing at the moment in codes which gives you there's no codified lateral system, neither for wind nor for for seismic. You can only do cantilevered columns. You can do braced frames in Canada, but in America you can only do cantilevered columns. So obviously it's you need to do testing and actually show that the system works. And the Framework building is going ahead really well. A lot of the fire testing is being carried out. So besides just the structural and the seismic resistance, you also have to, the fire is also something where the authorities want specific testing. That's going ahead, and we're meeting all the requirements. The one in New York is about 6 months behind, but also moving forward. So these are like they're almost demonstration projects for the industry, for us as designers, for architects, for engineers, for students, to show that these projects are possible. And also we need to demonstrate and prove that these solutions work for acoustics. This is the project that we're doing in Amsterdam. It's a 10-story tower where the fire protection system, acoustics, vibration, and all these other factors, to show that there's solutions out there that work. But mainly, we're doing a lot of research. Like I mentioned, understanding how these, for example, CLT, which is a new product, which is now in the IBC, but there's only one manufacturer in the States, up in Oregon, D.R. Johnson, and so how it actually behaves in fire is not completely known. The individual, the material itself, CLT, yes, but what happens when you put it together? What happens when you support it on glulam beams? What if you have two CLT walls and a CLT ceiling? Is there any heat that radiates and fuels the fire on the walls? So all of these different assemblies have to be understood, especially because they influence the insurance, right? The insurance industry, which insures buildings. If you're coming up with a completely new solution, you're going to get high rates, and so clients developers aren't that interested. But luckily, the NFPA, National Fire Protection Association, is funding research to better understand how it actually behaves. And most of the results are very, very positive, right? Mass timber, it forms a charring layer. You can't. The typical example is always you got to throw kindling on a fire to light a fire. You can't throw a massive log on it because it'll never really start. And so glulam and CLT behaves that way in forming that thick charring layer and protecting the rest of the material, which then you size for the structural demands. And research in seismic systems. Right? If there's nothing in the toolbox of designers, if there's nothing available, then we're teaming up with universities, especially up in the Pacific Northwest, to look at systems using CLT and other engineered wood products for lateral solutions. So one is, for example, a post-tensioned rocking wall. Yep, so you've got the CLT panels and you've got the post-tension cable in the middle, which then basically ensures that it goes back to its original position after having displaced after a seismic event. Or one that I was involved in, and we finished the initial testing just a couple of months ago, is a heavy timber BRB. Right, BRBs already exist. It's a buckling restrained brace, so it's a certain system which exists as a steel solution. But we're applying that kind of principle and that idea, and actually using a heavy timber version of it, where we have a steel core and a glulam casing, and the casing ensures that the steel core does not buckle. So trying to put even more possibilities in everybody's toolbox. And so for that, we just did some proof of concept testing. We teamed up with a manufacturer and a university, the University of Utah, put together some specimens, and these are the results of the different variations that we tested. On the left, you can see that one failed because it buckled. The sine wave. The one on the right, you can see failed because the steel actually tore apart, and so it failed in tension. That one failed in compression, and then the third specimen that we had actually worked and resisted the 100 kips that we were aiming for. So to finish off, I think, thinking about hybrid. Combining materials that maybe hadn't been combined before. For example, the laminated veneer lumber, epoxying bars into the wood, and then covering it all with a layer of polyurethane to protect it, right? That was bringing different industries together which hadn't worked together, and saying, you know, force them sometimes to work together. The composite solution for the life cycle tower. I think, Mark, you mentioned this, you know, this is a new team member. This is the CNC robot for the Metropole parasol, and we had to, you know, actually take him in as a team member and think, look, you know, we're passing the information onto a robot. You know, that robot was working for 365 full days in cutting out all of our elements. So, you know, as different technologies emerge, different people actually, and computers and robots are joining the design team. And something that I learned at the latest timber conference is going to the level of nanotechnology, and actually saying, okay, well, wood is wood, but why can't we try to change it and actually put some metal in there and make it magnetic, or make it transparent, and how can we use these changed material properties in the designs that we're looking at. That's on the nano, on a molecular level. But I also then walked by a nail manufacturer, and he's like, no, nails out of steel? Yeah, everybody thinks nails are out of steel, but actually we can make them out of oak. I'm like, oh, wow. So sometimes very difficult and very tricky and very research intensive challenges are what we need to go for, and sometimes it's just questioning things that we accept as normal but can actually be made carried out in a different way too. And then maybe you know, on the timber front, someday we'll actually achieve heights in our projects and complexities that Mother Nature has arrived at, but we still have a long way to go. And that's it. Thank you. And so I think, any questions?
Thank you.
Oh.
Wondering if there are any questions. In general, thank you. This is amazing to see your perspective, because it's a very different perspective than we attain. I think a lot of our students are actually thinking in wood, because we constantly bring it up in desk grids and discussions, because it is a future material. It's already widely used in Europe. It's emerging here in the US, and I think the possibilities are quite amazing, because you get like results 30% of the weight of concrete or steel. You get similar results, and I know a lot of our students are thinking in CLT or wood in their projects, and we do have engineering faculty in our studios that are facilitating that.
Yep.
I'd be curious. I have one question. I'm always curious when you build stuff, you put all this stuff into, I mean, like in a project we did, there's like this rubber foil you put around the building to seal it, and then I have a rubber band. The rubber band survives 2 weeks, and then it is rotten and actually pulls apart. So you're using resin and certain materials that the life cycle or the length of a chemical bind. Is it as trustworthy as a concrete wall or a piece of wood? I mean, that to me is always baffling, that you have chemical products in buildings.
Yeah, yeah.
And you're not really sure how long they last.
Yeah, yeah.
In the 70s, they told us, oh, the glue lamp binders last forever, and now buildings are falling apart.
Yeah, or in the 60s, they said concrete will last forever.
Yeah, it's true.
And then the rebar starts rusting, and yeah. So specifically the polyurethane for the Metropole parasol, that's exactly the question that the client asked us. And we also asked the manufacturer. In this case, it was Bayer. And their answer was, well, we've never really used this in this kind of application. So what answer do you, theoretically, it'll last forever. So polyurethane is actually a very stable, very durable chemical. But for this, they said 50 years. Like, okay, 50 years is what the client actually gave as his minimum. And then we put an additional coat of UV protecting paint on top of it, right? To at least, definitely protected from UV. And most importantly, we gave the concessionaire, who is maintaining it for another 35 years, a maintenance book for not only the polyurethane, but also for the connections. With the epoxy, we're pretty, epoxy resin is very durable, and it's also inside of everything. But generally for the connections, slip, and the polyurethane, we're telling them, every 5 years, go around, inspect, make sure there's no pinholes or openings. And what we also did is we put 2 samples up on the roofs of the buildings, and one of them we're going to open up in actually about 3 years and look at, how's the polyurethane holding up, what's the wood inside it actually look like. And then the other one we're going to open up 15 years down the line. So to actually have a bit more data without having to go into our structure. Because it is something where there's no certain answer.
So it's really pushing the envelope of what is actually construction, and I think that's very interesting. It's also, I think it also influences the idea of architectural construction, because you're applying basically robotic tools, CNC mills, and as we're using these software applications in the design process, stuff like this becomes more and more common, that you actually have a design problem that can only be solved through parametric solutions. Although it doesn't necessarily have to look parametric like the Metropole parasol, which is interesting because this thing could as well be a clay sculpture. Actually, the form is not what's parametric about it at all. It's just, it's mainly the manufacturing process, and that's interesting, I think. And that's also what we're getting at. We have projects, student projects, that don't look like anything parametric, but then all of a sudden there's a parametric aspect
of it, where you notice it,
Any questions from the students, maybe?
Yeah.
Thank you. The portion that I missed was basically the connection of your cores of this specific project to the ground. I missed that portion. If you could basically elaborate more on that.
Oh, okay, yeah. Well, that could take another 15 minutes. It was actually quite tricky because since they had found the Roman ruins, the archaeologists on the project actually said, well, you can only put foundations here, there, and there. So we only had 4 positions where we could actually support the structure, which is also, and they were built beforehand, or they were kind of built as soon as we won the competition. They said, okay, well, we need to start doing something, so we're going to build the foundations. And that actually also led to us coming up with the timber solution, because it's a more lightweight solution, because we had to work with existing foundations almost. So basically what happens is the timber comes down and sits on a concrete plinth, and that concrete plinth sits on a pile cap with, and then we have 3x3 9 piles going down through the soil. So yeah, that was a pretty. It almost became a design criteria for the entire structure, those foundations. Yeah.
Any more questions?
Anything else?
Reed, you were kind of raising your hand earlier. I'm putting you on the spot here.
Yeah. Oh,
how large can the panels of wood be CNC?
The panels can be about 10 by 80, I think, is the size that they fabricate. 10 by 80 feet. That's for laminated veneer lumber. It's a large. It's on the large end. For the complete, it just depends on the facility that each manufacturer has. So, for example, here in the States, if you go to Boise Cascade or the Structure Lam in Canada, and you ask them, what size panels can you get for the LVL, they might tell you something, slightly. It's like CLT also comes in different sizes depending on the fabricator.
10 by 80, why so narrow? Because
it's, hold on a second, so it's about 4 meters, 4 by 15 in meters, so 3, it's more like 15 feet by 40 feet. Yeah, but it's definitely a rectangle. Yeah.
Okay. I was
Yeah.
just wondering because they're running this through for 80 or
Yeah,
45
So
feet.
they usually have a width,
and then they keep
and then
running it.
they take a trunk, and then they kind of unravel it like toilet paper. That's how they get the veneers. They put a blade to a trunk, then roll the trunk, and then they cut off these little veneers. And so the length it's a lot longer than the width.
The width.
Yeah.
And the CNC milling works with the robotic arm.
Yeah,
basically.
yeah. It
So
sits
the-
on a table, and the table moves in 3 directions, and the robot arm also has 3 axes. So it's
That's interesting.
yeah.
It's always amazing to come to Arup because you guys are actually working, or other engineers, but engineers are working more at the forefront. They're actually pushing the boundary more than we do for our design work. But I think it's really interesting to see, and it's always enlightening. I mean, we usually, when you work on a project, you think of certain things, and then you meet an engineer, and then that engineer opens up a whole new world of what is actually doable or where you can push the project. And you realize that that there's a certain constraint that's in gravity, because everything wants to go to the center of this planet. But then the constraint can actually open up a whole new world, and that constraint becomes something actually very interesting. I think this project shows it.
Yeah.
Because when I saw the competition result, I thought, yeah, okay. But when it then was constructed, it was quite interesting.
Then the final, yeah.
Much more
Well,
compelling.
yeah, and what you mentioned about, that goes both ways, right? When, sitting together with 10 engineers, we discuss things, and then you
Yeah.
discuss the same thing with an architect, and you're like, oh, wait a second, it also opens up different possibilities.
Another question?
So we were whispering quietly in the back. How did you address the flammability with aspects such as the resin and the wood and
Yeah.
the code issues?
Yeah.
And then the other part is also when you slip the panels in, were they hoist? So this is the construction aspect,
Mhm.
where we love the nitty gritty. So are there cranes
Yeah, that is-
around and the sequence of that
So-
construction?
Let's go. So the issue with fire, it was a performance-based approach. Where a fire could actually start, how it could propagate, and the evacuation times. Generally, due to the height of the structure, it has no, it doesn't need a fire resistance. Generally, the structure is also very highly redundant. So if there were, for example, a very local, almost like an explosion or a large fire which did reach all the way up and burned 2 or 3 elements, the loads would immediately just redistribute, and the entire structure wouldn't collapse. So for it to achieve collapse, you need a very large area of the structure, actually. The other thing is propagation mainly would happen at the plaza level and at the trunks vertically. So that's our fire protection, right? That's a steel formwork for sprayed concrete, which is a certain height. I think it was about 4.5 meters high, to ensure that any kind of fire that happens on the ground wouldn't actually propagate it up into the timber structure. And at the top, due to the cafe and possible fire actually going out, around the central area there is an additional deluge system, which basically would flood the timber structure and make it so wet that it wouldn't then, because the polyurethane under fire is really bad. It forms droplets, and so in any area around that raised plaza, we have that deluge system to actually just wet the polyurethane so that it doesn't form droplets.
But the thickness of the wood would actually make the structure sound, because the polyurethane will burn off and then the wood wouldn't burn through, right? That's
Yeah,
what you
yeah,
said- as you
yeah,
showed
yeah,
in
yeah.
the examples. In the research.
And even if it would, that would take, by then everybody would be evacuated. Yeah.
I'm
was-
actually surprised that the wood industry, that there's so much funding for research on CLT. I thought this might take another 10, 20 years till it catches on in America. It sounds like, from what you were saying, it goes much, much faster.
That has changed in the last 3 months, maybe?
Oh, wow.
Yeah, so that's very, very, that's very recent. Definitely due to the fact that the USDA has, announced those 2 demonstration projects, the wood industry itself. So it also if you go into the Pacific Northwest and also the Georgia, where they have a lot of southern yellow pine, they're noticing that their rural communities are dependent on the forestry. So it's being pushed at a state level also to support the wood industry, and CLT is a product which just uses fir or pine or spruce, cheap material, but a really good product out of it. And so now, and German manufacturers are coming over and selling their product here for cheaper than the American manufacturers. So the market is also working, and all that together, they're now really pushing to do that testing.
Yeah, there are many benefits.
Yeah.
Plus, it's ultra sustainable because it has a very it has a zero carbon footprint basically, and that's something to think about too, because concrete and steel actually has a very high carbon footprint, so that's going to play more into the construction industry. So something to think about.
So recently, the concrete industry did post a video on their YouTube channel talking about the danger of wood. And the wood industry was like, "Oh, awesome! If they're paying attention to us, that means that we're really, we've really reached a certain step." It was kind of stupid, the video, but yeah, it's gotten that far.
It's interesting.
Yeah, it's come that far. Anything else? Any other nitty-gritty questions? Wait, you had two questions, didn't you? Not the fire and the erection sequence. Yeah. Sorry. So that was, on this one you can see it, right? So, the elements are all of a different length, and so as much as possible they were constructed, adding on, but at some points you did actually, with the crane, have to come above and slip the element in. So and that one's kind of a mixture if you can still reach it from the side. So a bit of slipping on from the side and some of them slipping in from above.
And because of the size of the structure, it needed to have metal connectors. It couldn't be wood, or what was?
We tried just all wood, but that would not have been enough to actually transfer the
smaller structures that would actually work.
For smaller, it would work. Geometry-wise, we would have had even more, a purely compression structure. But yeah, for these dimensions and sizes,
I'm asking for a student who doesn't dare to ask. Okay.
Yeah.
What's the weight of each panel?
The heaviest element. The heaviest one would have probably been one in one of the trunks. That number I don't know off. So the entire structure weighs 900 tons. I remember that number. I can't remember what was the maximum weight.
Which is about 900 middle-class cars, basically, smaller cars.
Yeah, and I'm thinking that one probably, that could weigh like a 1.5 to 2 tons. Weight of a car, yeah.
2 tons is a very nice car.
Yeah. Okay, more questions? Okay.
So if there's no more questions, we
all right, we can go
into election night.
Yeah. Well, thanks for coming, everybody.